Some of you, if you took AP Calculus, your AP Calculus teacher might have taught you this trick at some point in time. I know I used to teach my AP Calculus kids this trick, but I can't speak for all teachers. It's not officially on the AP AB test. So if you know it, great, you're lucky, and if you don't know it, you get to learn it today. Okay, so the question is where does this integration by parts formula come from? So the most complicated technique that you learned in Calculus 1 was the substitution rule, right? What rule did that thing kind of reverse? Reverse the chain rule a bit. This one's going to kind of reverse the product rule. That's where it comes from. So that's the formula that's at the bottom, like sort of like the center of your page. I'm going to show you where it comes from. So it comes from the product rule. And I find it easier. For some reason, this formula uses U's and V's. I'm going to start with F's and G's and then go back to U's and V's at the end. The packet's at the front. So what's the derivative of f of x times g of x? What is the product rule? F prime of x, g of x, great, plus f of x, g prime of x. Awesome. Okay. So that's the product rule. Now what we're going to do is we're going to take that product rule and we're going to integrate both sides. So integral of the derivative of f of x, g of x, dx equals integral of f prime of x, g of x, plus f of x, g prime of x, dx. Okay, so we're okay, we took the product rule, we're just going to anti-differentiate now. What happens when you take a derivative? So in this thing, I'm taking a derivative, and then I'm finding the antiderivative. What's that do? They kind of cancel out, right? And you just get f times g. So that's just going to be f of x, g of x. And then on the right, when you have an integral of two things added together, you can integrate the first term and the second term, right? Kind of like integrating x squared plus 2, right? You can integrate x squared and integrate 2. So you have the integral of f prime of x, g of x, dx, plus the integral of f of x, g prime of x. So far, so good? Okay. Now what I'm going to do next, I'm going to solve for this guy. As in get it by itself, just like solve for means in, Algebra 1. So to do that, I would take the first integral and subtract it to the left side. Does that make sense? Okay, so I'm going to end up with f of x, g of x. Oh, and I made a bit of a boo-boo. Can you tell what it is? This dx shouldn't be there, so scratch that. So sorry, it should have gone away with the integral. Copy error. Gesundheit. F prime of x, g of x, dx equals integral f of x, g prime of x. So is it fair to say so far nothing's been terribly difficult with that? Okay. Now what you're going to do is we're just going to make a small notation change. We're going to let u equal f of x, and we're going to let v equal g of x. And then does it make sense that you think that du is equal to f prime of x dx and dv is equal to g prime of x dx? Does that make sense? Kind of like when you do substitution? Okay, so replace everything by what I just said we're going to do. So do that and then see what comes out. Replace the f's by u's, the g's by v's. The f prime dx gets replaced by du. And I think you get uv minus integral, so the f prime dx, that's du, g is v, equals integral v, oops, equals integral u dv. Is that the same formula that's written above? Yeah, it's just reversed, right? It's just flip-flopped. So if I put integral u dv on the right, that's equal to uv minus integral v du. And the idea when applying this formula is that this integral on the left is something that you don't really know how to do, but when you do this transformation, the integral that you get over here is something you actually can anti-differentiate. And this works for certain kinds of products. Everything in this section is sort of doctored for either this technique to apply or substitution to apply, because you don't know any other techniques yet, okay? And there is some sort of, there's, I don't want to say pattern, but there's some general rules of thumb you use to pick what is u and what is dv in your integral and make this translation. So let's do one example and I can show you how it kind of falls out, and we'll talk about how you choose u and dv from that. I think it's best explained that way. Okay. So you have the integral of cosine 5x, x cosine 5x dx. But 5x really should be in parentheses. My bad. So sorry. WebAssembly, you're wrong if you don't put it in parentheses. Yeah?
Okay, so is x its own function?
X is its own function,
Okay.
and so is cosine 5x. So to use that formula, which is integral u dv equals uv minus integral v du, you take your original integral and you identify one function that is u and one function that is dv. And usually you choose u to be the thing that when you take its derivative, it goes away. Like the derivative of x is 1, it kind of becomes an easier constant, right? If it were x squared, that kind of eventually goes away after a couple derivatives. So let u equal x, and the rest of your function, the dv part, is the dv part, is cosine of 5x dx. And everything in your integral has to be accounted for, so you can't, like, leave out various pieces. Okay, so to apply this formula, this integral is equal to u times v. V is the original function. dv is the derivative of that function. So how would you find the function v given its derivative? Find the antiderivative, which in this one we'll be able to do kind of quickly. So what's the antiderivative of cosine of 5x? 1 over 5 sine 5x. You see why I had those, like, good to take the antiderivatives of these kind of substitution problems pretty quickly? Okay. And then if you have u is x, how would you get du from that? Dx. Take the derivative, it'd be 1 dx. So really what they're just saying here is u means original function, du means derivative of original function. That's really all this notation means. Yeah?
Why would you put the dx there?
Why would you put the dx there? Because we're going to need to know what du is to plug it into that formula.
No, I mean, you put the 1 there, but why did you put the dx?
Because technically taking the derivative of u is du dx equals 1.
Oh, okay.
Yep. Okay. Awesome. Okay, so now we're gonna use this little table of things to translate this integral using that formula. So uv is x times a fifth sine of 5x, and you take away the integral of v du, and in for v goes 1/5 sine of 5x. And then what goes in for du? Dx. And then is the thing that you still have to integrate, is it something that you can actually do?
Yes.
Yeah, pretty easily, right? So we have the 1/5 x sine of 5x just has to kind of hang around, minus the 1/5 that's already present has to factor out of the integral, times another 1/5, and that's going to be, is it negative cosine? Yep. So can I just change this to a plus? Okay. And then don't forget your plus c. So your final answer is 1/5 x sine of 5x plus 1/25 cosine of 5x plus c. And I'll try my best in class to put parentheses wherever WebAssign is going to make you put parentheses so that you don't like go to that and get it wrong because you just didn't have parentheses in the right spot. You will have put parentheses around that 5x in WebAssign. For me, I'm not going to dock you, okay? But WebAssign will. They'll say you're wrong when you're kind of not, okay? Yes?
So in the integrated equation, you have x and then cosine 5x, which are as you're splitting.
Yeah?
But when you substituted u and v for that,
Mm-hmm.
u is x and v is not cosine 5x.
That's because the cosine 5x is dv. So the way you can make this transformation is you identify parts in your integral, one part that is u and one part that is dv. And so in order to express it as uv, you have to take the part that's dv and figure out what v was. Okay, let's do it a question two. So orange shirt?
Yeah, so is that kind of format okay for you? Do you want it more simplified in terms of?
Oh, you do not have to do any kind of taking out greatest common factors or stuff like that unless I ask for it, so don't worry about it. Is that what you're asking?
Yeah.
Yeah, no, you're all good. Technically, the C, messes with all that all the time, right? Because you can't take a GCF out of that. So you could say never again. I won't make you do that. In general, I make you distribute in this class. Okay, yes?
Do you care if we put the equal sign in and forget it?
You should try to use equal signs as much as you can. I have to talk to Professor Fodry about what our policy is going to be on that, because we just have to agree.
All right.
I plead the fifth for now. Okay. In general, I'm going to try to not be a hypocrite. If I do it in class, you can more or less do it like me, like I'm maybe not as neat as I could be because it's talking and multitasking is challenging. But in general, just try to keep things readable and use equal signs when they're appropriate if you can. Try another one? Okay, let's try another one. All right. So that formula was integral u dv equals uv minus integral v du. Okay. So you usually pick u to be the thing that goes away with repeated differentiation. So does e to the x sort of go away with repeated differentiation? No. So probably going to let u equal x squared. And what part's going to be your dv? The rest of it, e to the x dx. And by the way, the thing you pick for dv has to also be something that you can actually anti-differentiate. If you can't anti-differentiate it, you can't get the v out of it, right? So we'll have an example like that soon as well. Okay, so what's the derivative of x squared? 2x. We'll say 2x dx. And what's the antiderivative of e to the x? E to the x. Okay, great.
That was my favorite.
That one's everybody's favorite. Yes, I think it is. So equals uv, so x squared, e to the x, minus integral v du. Can I pull that 2 out in front right away? Is that all right? So 2x e to the x dx. Dun dun dun. Do you know an antiderivative of x e to the x?
No.
No, but this is a process that can be reiterated. You can do it again. So you repeat one more time. U will equal, so you're looking at this integral now, u will equal x, du is equal to 1 dx, dv is e to the x dx, and then v is equal to e to the x. Okay, When you're working out WebAssign problems, you can be as sloppy as you want. When you're working out problems that are on like your take-home quiz, you have to write things nicely and the steps have to follow from each other. So I know it's tedious, but you've got to copy that x squared e to the x down to the next line, okay? Like on the stuff you're writing for me, which is like 10 problems, you can do that. WebAssign, I don't see your work, I don't care. -2, and be careful because this, we're going to expand using the integration by parts formula. So the thing that is one term becomes a thing that has two terms, which means you need parentheses. So parenthesis uv x e to the x minus integral v du, which is e to the x dx. And now have you reduced it to something that you can actually easily anti-differentiate? Yep. So we're gonna have x squared e to the x. I'm gonna distribute my -2. I'll have plus 2x e to the x. Oh no, I won't. I was testing you guys. What should I have there instead? Minus. Whoa! My eraser was bigger than I thought it was. -2. Okay, there we go. Recovered. X squared e to the x minus 2x e to the x. And what comes next? Plus 2e to the x. And then plus c, of course. How could you, if you were really, really, really anal, how could you, or back in the day when I didn't have Wolfram Alpha, because I was in college like, I don't know, God, 14 years ago, when I took Calculus 1, how would I have checked my answer? Take the derivative. Like on your test, you got spare time and you had to use integration by parts, start taking derivatives and see if they're right. Yes?
Were you only distributing the 2, not the negative?
The negative got distributed as well, which is why this last term became positive.
Yeah.
Yeah.
But like in the formula, it's uv minus the integral of that, and you just took out the 2 there.
Just took out the 2 there. Okay, so let me see if I can get to the crux of your question. So this 2 came up in this step, right?
Yeah.
When I expand, like it's just this part that becomes this. Does that answer it? Okay, great. Awesome. So the 2, you could have, moved it inside and incorporated it, or you could, I just choose to leave it out and distribute it at the end.
Yeah, I just
Yeah.
So why doesn't the negative distribute to the c?
Because c is an arbitrary constant, and so you can just rename it whatever you want. Like constant times 2/3, just call it a new constant. So you almost never, ever, ever do anything to c. It just be like the other constants get absorbed into c, and c just stays c. Because if you ever had to go find out what c was, like if you're given an x and y value of your original function, it doesn't matter that you've renamed it some other c. Yeah.
So you integrated twice. Why didn't you have a plus c the first time you integrated?
Same kind of question he's asking. You could have combined your first plus c with your second plus c into a new plus c. Yep, good question. Okay. So we had to do integration by parts twice. If it had been x cubed, what do you think would have happened? I had to do it 3 times. And if it was x to the 4th, you do it 4. I think when I was in Calc 2, they made me do it 4 times once. My teacher was mean. Oh, TJ. Okay. So this one. So thus far, we've picked u to be the monomials, right? Things like x squared, x, y cubed. What is the problem with letting dv equal ln y? Do you know how to anti-differentiate that? Yeah, but you look it up and it's y ln y minus y. Is that right?
Yeah.
Yeah. Oh. And be impressed, make impressed noises.
I have no idea how they got there.
You know what? That's example number 4. Okay, somebody thought about this. All right, so you are forced to let u equal ln of y because you can't anti-differentiate it. And you're kind of like scared for a second, like, oh my God, is this going to work? So what part do you have to let be your dv? Y cubed dy. Integral u dv equals uv minus vd. Okay, alrighty. So what's the derivative of ln of y? Mm-hmm, great. And what's the antiderivative of y cubed? 1/4 y to the 4th. Okay, great. So this will equal uv, so 1/4 y to the 4th ln y minus 1/4 integral v du, so y to the 4th times 1/y dy. I'm going to add a couple things to that because technically right now it's like a little bit wrong, but is everyone okay with what went where? All right. Okay, so the first thing that's a little bit wrong with this is that the integral that I had originally was a definite integral. It had bounds, right? So because of that, the thing that no longer has an integral sign, it should have bounds on it. So this first bit right there, that 1/4 y to the 4th ln y, you should put the little bar that says 1 to e that tells me that you're still going to plug e in and plug 1 in. Okay? Where else do you need a 1 and an e? On the second one, 1 to e. Okay? But since that first part no longer has been integrated, it just is now being evaluated. Okay? Yes?
Could you put parentheses around the entire equation and then put a bar, or would that not work?
It's kind of not 100%, I understand what you mean. It's kind of not 100% correct because with the first thing, with the first thing you actually have it without an integral sign, the second thing you don't, so this way's a little bit better. Does that make sense?
Yeah.
Okay. Yeah.
So, would it be simpler to evaluate with the values there, or would that be stupid?
I'm going there. Let me finish, okay? So we're going to have 1/4. So the first part I'm going to evaluate. 1/4 e to the 4th ln of e minus 1/4 ln 1. So that's the first bit. How about that next thing? What does the integral simplify to? Because simplifies a lot, doesn't it? It's y to the 3rd, right? And you breathe a sigh of relief because can you anti-differentiate y to the 3rd? Yes, yes you can. Okay, so with that the first part of the expressions in parentheses, what does the first term simplify to? E to the 4th over 4. Great. Ln of e is 1 and ln of 1 is 0, yes? Okay. The next thing we're going to have 1/4 times another quarter y to the 4th from 1 to e. There are lots of ways to do this correctly, but you have to be a little bit careful with that negative sign there. So here we go. E to the 4th over 4.
Couldn't you just put it in parentheses and ignore the negative sign?
Yeah, I'm going to say 1/16, and then I'm going to plug this stuff into the y to the 4th, right? Yep. E to the 4th minus 1. Does that make sense? Okay. So I just kind of looked at this part alone, and then I can factor in the 1/16 or the negative and the negative later. So you have e to the 4th over 4 minus e to the 4th over 16 plus a 16th. And I suspect if you make any mistakes in this, once you get the basic idea, the mistake you're going to make is negative distribution and just silliness, basically. And then can you find a common denominator, at least combine those like terms that are the same? Like the e to the 4ths, right? So that'd be 4 over 4. So I think that would be 3 e to the 4th over 16 minus plus a 16th. Or you could say 1/16, 3 e to the 4th plus 1. Both are fine. I'm not going to require one over the other.
You also do 3 e to the 4th plus 9 all in.
Oh, exactly. That would also be fine. Yep. Your TA should be good enough to be able to identify that they're all equivalent answers. Yeah, Rachel?
And you don't
It's a definite integral. It's like had you included the plus c when you plugged in the first number and then the second number and subtracted them, the plus c's disappear. Does that make sense? Okay. All right. So just notice that with this question, I mean, there were two main points to it. Main point number one is how do you handle a definite integral? That's a little bit different, right? Only slightly. And the second point was that you don't always let your u be the x or y to a power. Because that is not always that way. Usually, yes, but not always, okay? All right. Question, ln of x dx. We're going to learn the antiderivative of this. And this is a clever application of integration by parts. And you should feel a little bit like there isn't enough here to do it, but there actually is. So what are you forced to let be your u? Ln of x, because you can't find the antiderivative of it. So what's the derivative of that? 1 over x dx. So what is left to be your dv? Just dx. And then to go backwards to v, you get x. So the kicker there is that when doing integration by parts, you can let dv equal dx. That's a legit choice, okay? So this equals uv minus integral v du. Okay. So uv is x ln x, right? Minus integral v is x, du is, okay, and well, what's x times 1 over x? 1. So x ln x minus integral of 1 dx is, because they cancel, yep, x times 1 over x makes 1, right? So that's x ln, I hate it when I don't write what I say, and then when my eraser goes and erases everything. X ln x. What's the antiderivative of 1? X. And just for kicks, let's actually check this one, okay? Let's take the derivative of x ln x minus x. I'm pretty sure that when I taught Calc 1 last, I made my poor Calc 1 students like do this derivative just because it entertained me that they would find the antiderivative of ln x. So how do you differentiate the x ln x part? Use the product rule. So it'd be 1 times natural log x, right? Plus x times 1 over x, right? And then what's the derivative of the negative x? Minus 1. And look, you have ln of x plus 1 minus 1 equals ln of x. So that is just verifying for yourself that that actually is the antiderivative of ln of x. Not obvious, right? No. So now that you have that, you can use it. Like example 5, you can use this formula to find the antiderivative of ln of other stuff. As in, you can make a substitution and apply the rule we found in example 4. It's like you could let u equal 3x plus 1. So this is just regular substitution. What is the du then? 3dx. So after your substitution, this becomes 1/3 integral natural log of u du. And then you can use the result from example 4. What's the antiderivative of natural log u? U instead of x, right? So u ln u minus u, right? And then the plus c can just hang out on the end. And then your last step just is to input what your u was. So 1/3 3x plus 1 natural log 3x plus 1 minus the quantity 3x plus 1 plus c. And there's various things you can do with that to simplify it, but whatever, this is good enough. I'm not going to make you memorize that integral of natural log formula because I just think what's more important is that you understand where it comes from. So what I could ask you to do in a test is like to say prove that this thing is, like, you know, derive what it's equal to. Does that make sense? So memorizing it means you'll know what you're supposed to get, but the where it comes from is more important than memorizing that random formula. So, and that trick where you let dv equal dx applies to other stuff too. It applies to lots of inverse functions actually. So the next one, you see how ln is the inverse of the exponential, right? Next one we have inverse tan. Yeah?
The last one, could you also do integration by parts? It'd just be more complicated.
It'd be more complicated, yeah. I've tried it that way and it just ends up getting kind of messy. So it is usually, it's easier to substitute. But using the same technique as the previous problem should work. And your answer might look different because there's some combining of constants that happens, and like the constant that was present in the example that I did gets sucked into the plus c if you work it out the other way. But it will work. And I'd be able to figure out that they were the same answer. I would just be puzzled for a second, but I could figure it out. And WebAssign should be smart enough to also catch that. Like it is, it got a lot smarter than it used to be. So like it is better. And so if you think you're right, you can message me that you're right, and I'm happy to check. Usually it is the case that you're wrong, but occasionally WebAssign has been fussy about syntax, and I've caught that via students asking. So there's the little ask your teacher button, and if you use it, I'll answer, or somebody will answer. Because Jill Fodry and I, they're mushed together, so she might answer too. But somebody will answer you, eventually. Hopefully quickly. But not at 11 o'clock at night. I'm sleeping. Okay. So same sort of strategy. You don't know how to anti-differentiate inverse tangent, right? You know how to take its derivative though, yes? At least you're supposed to. So u is inverse tangent of 2x. What's left over to be the dv? dx. Okay, so v is obviously equal to x. du. What rule do you have to use in taking the derivative of inverse tangent of 2x? The chain rule, yep. So the derivative of inverse tangent of stuff is 1 over 1 plus stuff squared, right? So there's the 1 over 1 plus stuff, the stuff is 2x squared. And then multiplied by what? Because the chain rule, 2, so to say times 2 dx. So really that's 2 over 1 plus 4x squared, right? Okay. So just to simplify it, du is 2 over 1 plus 4x squared dx. Okay. All right, equals uv minus integral v du. So x tan inverse 2x, 0 to a half, minus integral 0 to a half. When I multiply v and du, I'm going to be a little bit quick here and say that it's 2x over 1 plus 4x squared dx. Is that okay? All right. Okay, so let's start, we'll plug in stuff in the first bit. So that's 1/2 inverse tangent of 1, because 2 times a half is 1. Plugging in 0 gives us 0, because it's 0 times something. I doesn't remember what the something is, still 0, right? Okay. Now this second integral, that's not like super easy to anti-differentiate, is it? Because it's not an obvious thing like sine or e or a polynomial that you can do like right away, right? So what might happen is when you do this, the resulting integral might rely on a different technique you've learned, and what's your only tool in your pocket besides just knowing what it is? Substitution. Okay, so this one will require substitution to finish. And here's one sort of just semi-technical bit. You've already used the letter U, so you shouldn't use it again. Does that make sense? Because your U means something, you don't want to give U the same name. So when I took Calculus 1, my book did W substitutions, and probably because they were looking ahead and thinking, oh, they're going to use U later, let's make them use W all the time. Okay? So what are you going to let be your substitution for that second integral?
2x.
No. No. 1 plus 4x squared. Right? And then its derivative appears there. And then, of course, you get to like relive your childhood days with Arthur as you say, dw equals, sorry, 8x dx. Okay. Oh, and because it's a definite integral, you should change your bounds, right? So if x is equal to 0, what is w equal to? 1. Yep, plug 0 into the substitution for x. And if x is equal to a half, w is equal to 2. 1 half squared makes a quarter, right? So that becomes the integral from 1 to 2 over 8w dw. Where that over 8 ends up isn't super important. Well, kind of important. Is where the over 8 comes from make sense? Because that came from the fact that dw was 8x dx, right? Okay. So,
Why is it 8W?
why is it 8w in the bottom?
Yeah.
You understand? It's okay, I can do it more slowly. And actually, I could also have written it like this. Let me try it this way and see if that makes more sense. What if I wrote it as 2 over 8 over w? Is that okay? I should say dw. So the reason that is because at this stage, you found dw was 8x dx. So then solving for, you have the x and the dx, right? Okay. And any of us going to become a quarter, and we're going to pull it out of the integral. Is that all right? Okay. Oh, and by the way, you should know inverse tangent of some things. Can you find inverse tangent of 1? What angle, when you plug it into tangent, gives you 1? Pi over 4. So a half times pi over 4. We got minus a quarter, integral 1 to 2, 1 over w. So what's the antiderivative of 1 over w? ln w. So you got pi over 8 minus a quarter ln w from 1 to 2. So that's pi over 8 minus a quarter ln 2 minus ln 1. And ln of 1 is 0. So that's pi eighths minus ln 2 over 4. Of course. And I know you've got a question, but one more thing we say quick before I forget it. WebAssign always wants exact answers unless it otherwise states that it wants an approximation, which means you have to give it this and not a decimal. Does that make sense? It's okay if like your answer is 1/2 and you give it 0.5 because 0.5 is exactly 1/2, right? But if the answer is 1/3 and you give it 0.33, 0.33 isn't actually 1/3, right? It's 33/100, which is close to a third, but it's not a third. So give exact answers unless otherwise specified. It will tell you that you're wrong even though you're like only wrong in a very minor way. Okay? Yeah.
Okay, so your original bounds for your integral were 1/2 and 1. Why did it go to 2 of them?
Because I made a substitution and those original bounds are x values and I have to change them to w values. Yep, and so you get those by plugging the x's into the substitution that you're making. Yeah, Mary Kate? What happened to the x? Oh, okay, let me pull this down a sec and you'll see. So the x, so does it make sense, first of all, that 1/8 dw equals x dx? Is that okay? Yeah, that's all right?
Oh, okay, yeah.
Okay, and then the x and the dx, they get replaced by the 1/8 dw.
Okay.
Anything else? Good to go? Okay. All right. I really want to let u equal x squared, but that probably isn't going to work. Just because you can anti-differentiate ln of x, I wouldn't in general try to do so. Does that make sense? Like, you know a formula, using it is not going to make your life easier usually. Okay? I'll say usually because there might be an exception where it will, but in this case, no. So what do you think you're going to let u equal? Unfortunately not. If it weren't ln, like if it were e or something, then it would work out okay. But when it's, do you know how to anti-differentiate ln of x squared?
Okay, so for you want the one that you can easily anti-differentiate.
For dv is the one you easily anti-differentiate. Yep.
Could you substitute a variable like w for ln of x, just because there's two functions going on here?
I don't think it's going to do any good. If you let I don't think it's going to help. If you want to try it and see what you get, go for it. But I don't think that's a good idea. Okay, theoretically possible, sure. Going to help, probably not. And I think actually for that substitution to work, you have to have the derivative of ln x show up in the integral, and the derivative of ln x is 1/x, and that's nowhere present. So yeah, I don't think it's going to work very well. So what's left to be your u? Natural log of x squared. And there's no hard, fast rules that, this always works, this always doesn't work. You just have to, these problems, try something. That's why there are those suggested problems on like the bottom of the notes. You can just try picking u and v and c. They should fall out within a couple steps usually. So the easy one, what's the antiderivative of x squared? 1/3 x cubed, yep. Okay, how about the derivative of ln of x, the quantity squared? 2 ln x, and then times 1/x from the chain rule. So it's 2 stuff to the first times stuff's derivative. Okay? Oh man, see how you have to know Calc 1? You can't forget about those derivatives, right? You're already in trouble. I wasn't lying on the first day. Okay, so uv 1/3 x cubed ln of x, the quantity squared. Hello.
Tried to have them once.
It's all good. It won't ever happen to me because I don't have one. Haha. Okay, minus. Okay, so can I pull the constant out in front right away? Yeah, so what's the constant going to be? 2/3. The 2 from the du and the 1/3 from the v. Integral ln x times, and now let's just get a little bit faster at this. If I multiply this and this, what's the power on my x going to be? X to the second, because you have a 1/x in du, and you have x cubed in v, right? X cubed times 1/x is x squared. Okay. Now, you're not done, but is the thing that you now have to anti-differentiate something that you can actually do? We did one a lot like that, didn't we? I think I had like xy cubed ln of y, which effectively is the same thing, right? So take take a minute or so and try to figure out this one. What's your u going to be? What's your dv going to be? See if you can get it. I'll take a sip of water and pause so I don't go too. Did everyone choose u to be ln and dv to be x squared dx? Okay. And then does your next step agree with my step? We got 1/3 x cubed ln x minus 1/3 integral x squared? Yes?
If we're changing U, why do we not change the symbol?
Oh, because I'm being a little bit lazy. You probably could call them U1 and U2.
Yeah, that's what I was thinking.
Yeah, so I won't be picky about that, but just because it just is tedious, I gotta go back to the others. So, it's okay. Yeah. We good? Okay. So 1/3 x cubed ln of x squared minus 2/9 x cubed ln x plus 2/9 times, what's the antiderivative of x squared? 1/3 x cubed, and then plus c. So your final answer is 1/3 x cubed ln of x squared minus 2/9 x cubed ln x plus 2/27 x cubed plus c. One semi-annoying thing about Wolfram Alpha is I think that they always factor stuff out. So like if you're checking your answers against Wolfram Alpha, you'll have to take a GCF out of your answer to compare to theirs. Is that okay? So it wasn't so bad, it was just 2 iterations, right? Okay. Now there are the last examples I have are some sort of more clever tricks. This first one's called Around the World. So do either of these functions go away when you take their derivatives eventually? No, e to the x's derivative is just e to the x repeatedly, right? And the derivative of sine kind of like fluctuates between cosine and sine, positive, negative, right? So, well, you have to pick something. So I'm going to pick u to be e to the 2x, and I'm going to pick dv to be sine x dx. It actually doesn't matter which way you choose. This way is just a bit easier than the other, and I can explain why in just a sec. So what's the derivative of e to the 2x? 2e to the 2x, okay. And what's the antiderivative of sine? Negative cosine. And I'm going to let this thing, I'm going to let, well, we won't start there. We won't quit that, okay. Give me a second. So I've got the original integral of e to the 2x sine x dx is equal to, so uv minus e to the 2x cosine x. So uv minus integral v du, so I'm going to say plus 2 integral e to the 2x cosine x dx. uv minus integral v du. And you say, well, whatever. So what would be your next guess? Do it again. Yeah, why not? Okay, so if you chose the e to the stuff to be the u in your first iteration, choose the same pattern in your second iteration, okay? So my u is going to be e to the 2x again. My du is 2e to the 2x dx. The dv is cosine x dx. V is equal to regular sine, right? So we have negative e to the 2x cosine x plus 2 times uv e to the 2x sine x minus 2 integral e to the 2x sine x dx. And you say, Beth, not fair. The stuff in the integral is back where you started, isn't it? So here's the clever trick. So before we apply clever trick, let's distribute everything, okay? So this is negative e to the 2x cosine x plus 2e to the 2x sine x minus 4 integrals of e to the 2x sine x. So these equal signs that are here, they mean something. They mean this first thing is equal to all this stuff that we have in the last step, right? So here's what I'm going to do to make our life a teensy bit easier. I am going to let I standing for the integral, equal the original integral we were given. And then rewriting, you know, I have this thing equals all this stuff. Do you see that that's the same thing as saying I equals negative e to the 2x cosine x plus 2e to the 2x sine x minus 4i? Does that make sense? Okay. And then you can do something that seems kind of like wacky and not like it's right, but it is right. You can move that 4i to the other I. So what's a single I plus 4i going to be? So it'd be 5i. Negative e to the 2x cosine x plus 2e to the 2x sine x. And then how would you solve for the integral? Divide by 5. So the integral would be negative a fifth e to the 2x cosine x plus 2/5 e to the 2x sine x. And then you're supposed to have plus c at some stage, so there's your plus c. It would have been slightly harder to let to flip the u and dv. So let's just briefly discuss why. So if I'd let dv equal e to the 2x dx, my v would have been a half e to the x 2x, and you would have had to work with fractions. Okay, it's not going to be wrong. You'll get the same answer. It's just that you might make a mistake along the way because the fractions introduce level of, they're not really complicated, but it's easier to make mistakes with them. Okay, so if you have a choice, that's why I made that choice. Okay. I'm going to start example 9 and then also 10, and you're going to have to finish them yourselves. They're a little bit clever. There's a clever trick you apply in the beginning that then you can do integration by parts after that. So I'll do the first steps of them, okay? So in your homework, these problems, like WebAssign, they'll say, first apply a substitution and then use integration by parts to do the integral, okay? So I'm going to use W. So I'm going to let W equal x squared. dw is then 2x dx. And notice in your integral, I can take that x cubed and I can break it into x squared x cosine of x squared dx. Okay, so what does this x squared and what does that x squared get replaced by? W. So W cosine W. How about the x and the dx? Not quite. They get replaced by half dw. But dw is quite close. That'd be 1/2 out in front dw. And is this now a thing you can do integration by parts with? Yeah, you would let u equal w, right? What would you let dv be? Cosine w dw. So from there, you should be able to get it, okay? And that one's a reasonably straightforward substitution. The next one is like really, really quite clever, okay? So what do you think you're going to substitute for here? There's not many options, right? Well, if you change it, if you do x, you're going to become like integral sine of root w dw. Doesn't change much. So the root is inside the sine, right? So let's let w equal root x and just see where that leads us, okay? Same thing, x to the 1/2. What's the derivative of x to the 1/2? Half half x to the negative 1/2 dx, or as somebody said, it's 1/2 root x dx, right? Okay. So then solving this thing for dx, 2 square root x dw equals dx. Do you buy that? And then here's the clever bit. You've got two variables there, which usually is a problem, right? But what is root x equal to? W. So that's 2w dw is what replaces dx. So this becomes the integral of sine of w times 2w dw, or twice the integral w sine w. And is that now something that you can actually do with integration by parts? Mm-hmm. You would let u equal what? W. And what would you let your dv be? Sine w. But the tricky thing there is that you can actually like sort of seriously mess with the substitution a bit, right? If they're doctored to work, all right? And there is a question like on your take-home quiz and probably also in WebAssign, okay? But once you pick the substitution, the rest of it should sort of fall out and it becomes a more or less obvious integration by parts question, okay? Awesome, all right.